All right, Calculus 2 students. We are going to do some calculus when we're working with polar curves. We'll be talking about how to find tangent lines, area contained within polar curves, and also arc length of polar curves. The first skill that we want is we want to be able to express any point on it in rectangular coordinates. Take a point like right here, for example, and if you want to express this in terms of rectangular coordinates, we simply have to use the formulas we talked about in the last section. Let x equal r cosine theta and y equal r sine theta. And then we're going to use the fact that r is equal to 2 plus 2 cosine theta and replace both of these r's with that expression. And there is how we can write our point in Cartesian form and rectangular form. What we've effectively done is we've parameterized this polar curve because I'm now expressing x as a function of another variable and y as a function of another variable. This is exactly like what we did where we had x and y were expressed as functions of t. Now in that case, we sort of thought of t as time, as something that was geometrically disconnected from the image that the parametric equation produced. In this case, this is like a parametric equation, except there is a geometric interpretation of the parameter of the theta, and that theta corresponds to the angle that is being projected from the origin. But regardless, x and y are both now expressed as functions of some other variable, which means that all of the calculus formulas that we use for parameterized curves we can now use for polar curves. All right, so let's start putting this to use. We want to find the equation of the tangent line when theta is equal to pi fourths. I'm going to copy these points down and separate them and call one of them x of theta and the other one y of theta. So the top one here is x of theta, and then this one is y of theta. All right, so we're trying to find the equation of the tangent line when theta is pi fourths. Well, theta is pi fourths is this trajectory. Plug in theta into this expression. So in polar coordinates, this location is 2 plus rad 2 is the r, and the angle is pi fourths. What we're going to want to do is convert this to rectangular coordinates. We're looking for the x and the y coordinates. X of pi fourths, we do get the 2 plus rad 2, or that's just the r for that particular point, and then multiply this by the cosine of theta, which is rad 2 over 2. Distribution, we'll get the 2's canceling, leaving just a rad 2. And the second one, we'll get rad 2 times rad 2, which is 2, and then all over 2, so we get just plus 1. Y of pi fourths is going to wind up giving us the same thing, 2 plus rad 2 times rad 2 over 2, again giving us rad 2 plus 1. We know the points now that we're going through, but now we've got to find the slope. Well, to find the slope, we have to do the derivative dy dx, but since we're working with a parameterization, we just have to differentiate y with respect to the parameter and then differentiate x with respect to the parameter. So it'd be y prime of theta divided by x prime of theta. And we're going to use these functions to do these derivatives. So we're going to have to do the product rule in each case. Okay, well, let's first focus on y. Differentiate what's in the parentheses first, and we get negative 2 sine theta, and then times the second, which is sine theta, so that'll be sine squared, plus the first, which is 2 plus 2 cosine theta, times the derivative of the second, which is cosine of theta. Okay, and that's over. Now we're going to differentiate the x function, so again, the product rule. The derivative of the part that's in the parentheses is negative 2 sine theta times the second, which is cosine theta, plus the first times the derivative of the second, which is negative sine theta. So I'm just going to make this be subtraction here, sine theta. Okay, so here we have an expression for derivative in the traditional sense, dy dx. And if I want to find specifically the slope of the tangent line at this point, then I just have to plug the correct theta in. Slope of the tangent line will be y prime of pi fourths divided by x prime of pi fourths. Sine of pi fourths is rad 2 over 2, then square that. That's going to be 2 fourths, which is the same thing as 1/2. Times that by that negative 2, so we're going to get a negative 1 to start, plus 2 plus rad 2 times rad 2 over 2. The bottom, sine theta, cosine theta are the same, so we get rad 2 over 2 times rad 2 over 2. That gives me 2 over 4, which is 1/2, and then times that negative 2 in front. So again, a negative 1 to lead off. And then this time we have minus, and then again, this will be 2 plus rad 2 in here, and then another rad 2 over 2. So we have negative 1 plus rad 2 plus 1, and then we have a negative 1 minus, and then parentheses rad 2 plus 1. The top just becomes rad 2, and the bottom becomes negative 2 minus rad 2. Okay, so there's the slope of the tangent line. And now we get to construct the equation of the tangent line. This is your x sub 1, and this is your y sub 1. Use point slope form to construct the equation of the tangent line. Y minus 1 plus rad 2 equals the slope times x minus the x coordinate, which is also 1 plus rad 2. And we'll call this good. I'm not going to isolate the y. Let's confirm a lot of the stuff using Desmos. I'm going to open up that polar curve file that I was working with in the last unit. As this thing is drawn, it makes our limacon. If you want to see the entire limacon, we could just change this capital T here to a 2 pi, and then manually type in pi force for capital T. Why don't we just type in our answer that we got and see if it looks like the correct tangent line? Y minus parentheses 1 plus square root of 2 end parentheses equals square root of 2 divided by negative 2 minus square root of 2 times x minus parentheses 1 plus square root of 2. And sure enough, we did indeed find the line that was tangent to this polar curve at that point. Okay, we did that one by hand. Let me show you how to do this with the technology. Create capital X and capital Y functions. Capital X of t equals r cosine t is what I want to type in here. But r was defined by the function f. So f of t will give me the r, and then times that by cosine of t. And we don't care to see that graph. The next line will be similar. Then we want to put them together as a point. Make that 0 to capital T. This parameterization will graph the polar curve as well. So let me hide the simple polar curve. Now we're seeing the purple one, which is the parameterization, and then I'm going to play capital T. In order to do that, I'm going to have to get away from that pi force, put a number back in there, and then you should see the slider come back and play that. So this parameterization also produces the limacon. And let me just hide this image. We don't need a duplication. And then the slope of the tangent line is going to be equal to capital Y prime of, and then you can plug in capital T here, and then divide that by capital X prime of capital T, and this gives us the slope. And then to graph the line, I would just type in the point slope form. Y minus, plug capital T into the Y function, set that equal to the slope I just found, which we're calling M, times X minus capital X of capital T. Well, what's nice about this is now I can find tangent lines for all points by simply moving T around. And look at this, we're making tangent lines all the way around this limacon. The formula for arc length with parametric equations is just going to be applied here as well. We'll say that this is angle alpha and this is angle beta. And we want to figure out how long a polar curve is between these two angles. And that integral is going to be from parameter to parameter, so it's angle alpha to angle beta. And then we had the derivative of the x function with respect to that parameter, and then square that, plus the derivative of the y function with respect to that parameter, and then square that, and then take a square root of all that, and then d theta. This is one way to do it. There's another way to do it, and that one is also angle to angles. It's going to be r of theta squared plus its derivative squared, and then put all that in a square root. You can use this version of the arc length formula if you don't want to bother with converting to a parameterization first. Find the length of one petal of the given rose below. Use technology to evaluate the integral. One thing we're going to have to do is figure out the actual angles to draw one petal. And the way to do that is simply set the r function equal to 0 and solve this equation. Sine is 0 when the angle is 0, pi, 2 pi, etc. So that means theta itself, divide all these by 3, and you get a list of all the angles where the sine of 3 theta will be 0. The two I'm interested in are the 0 and the very next one, which is pi thirds. And that is the amount of angle required to draw one petal. The length of this one petal will be an integral from angle 0 to angle pi thirds. And let's do the parameterization version first. All right, so we'd have to do some parameterization. X is equal to r cosine theta, and then you replace r with this expression. Right, so x is equal to sine 3 theta times cosine theta. Of course, you would then need to differentiate that, and then once you get the derivative, you would then need to square that. The next one's going to be similar. We've got to do the same thing but for the y. So this needs to be the y function. So it needs to be r times sine of theta. Then you got to do the derivative of it, and then you got to square that derivative. And then you square root all that d theta. Let me show you the other way you could do arc length on this without converting to rectangular coordinates first. L is equal to an integral from 0 to pi thirds. And we just have to write down what the r function is, so sine of 3 theta, and square that. And then add to this the derivative of the r function. So differentiate just that simple thing. R prime of theta is 3 cosine 3 theta. And then that goes here, and then that needs to be squared. Then all of this needs to be square rooted, and then d theta. All right, and let's see what we get. We'll do it both ways. The capital F function is sine of 3 theta. L equals an integral. Let's do it with the parameterized version first. We're going to integrate from 0 to pi thirds. And we're going to integrate the square root of. Two things are going to be squared, and then outside of this. So if you don't want to keep typing out theta, you could just let little t stand for theta. So we want to do the derivative of the x function. So I could do this symbolically by just saying capital X prime. Then plus, do the same thing here, capital Y prime of t. Now let's do it the other way. Integrate from 0 to pi thirds, square root of, still have a structure of something squared plus something squared dt. And the r function was just f of t. And this one here is f prime of t. And you get the same length. Area with polar curves. In Desmos, if you actually put an inequality here, it'll do shading for you. So get rid of that equal sign and say less than. So now we get this idea that as the angle changes, we're sweeping out an area. And if you don't want it to start at 0, let's say we wanted to go from pi thirds to something, the lower limit would be pi thirds. Let's say we wanted to figure out this area here, that triangular wedge. It's not technically a triangle because one side is curved. Now, when we did area under a curve using rectangular coordinates, we did a whole bunch of skinny rectangles and we found out the formula for the area of one rectangle and then add them all up to get the total area. We do something very similar here, except we don't do rectangles. We do a whole bunch of little wedges as this rotates around. So we do integrate, adding up a whole bunch of areas of triangular wedges. Turns out that when you do this, and let's say this is angle alpha and this is angle beta, the area can be found by integrating from alpha to beta of 1/2 of r of theta squared d theta. Find the area of one petal of the rows below. Do this without using technology. Your challenge here is to figure out some angles where a petal starts and stops. And you could also use some symmetry. If you want to start at angle 0, then we just got to figure out the next angle where this petal will close off. And by symmetry, it does appear to be like it's going to be pi fourths. So if you want to do an integral from 0 to pi fourths, it's going to do all these little triangular wedges in there. It's going to find you the area of half of a petal. And by symmetry, you can then just double that answer to get the other half. As another option, instead of starting at the angle 0, let's find an angle where the petal actually starts to draw itself. Visually, it looks like that angle is going to be negative pi fourths. As we sweep from negative pi fourths to pi fourths, that should give us that entire petal. And we can also find out where the petals start and stop without technology. I just have to set that equal to 0 and solve for theta. And it would confirm that negative pi fourths and pi fourths are solutions to this. Since we're doing this by hand, let's also use symmetry, so I can involve a 0. Choose to just do 0 to pi fourths to get really just this area here, but then I'm going to double that answer. Area will be equal to twice an integral from 0 to pi fourths of 1/2, and then we just put the r function, which is cosine of 2 theta, and that needs to be squared. The 2 and the 1/2 just cancel each other. Now I just have to do the power reducing identity on this part, which generates another 1/2, and the rest of it was 1 plus cosine of, and then double that angle to 4 theta. So I could distribute the 1/2 and then integrate, or theta halves, plus 1/4 sine 4 theta, but then there's that 1/2 that's going to multiply to it, so it's going to be 1/8 sine 4 theta. And now we've got to evaluate this from 0 to pi fourths. You can see why it's nice to have 0 involved. So plug in pi fourths, it's pi eighths. 4 times pi fourths is pi, and sine of pi is 0, so that actually zeroes out. And then minus and plug in zeros, everything zeroes out as well. So the area is going to be pi eighths. And it's the total area of the petal. What the integral is doing for us, it's finding the areas of the triangular wedges as the angle varies from negative pi fourths to positive pi fourths, and then it stops. So we are indeed just finding the area of one petal. So whatever the units are, we should say square units here. Let's get into some slightly more complicated things happening when we have an inner loop here from a limacon. We're here to find the area of the inner loop, and we're just going to use technology to evaluate it. Finding the angles where the inner loop starts and stops. We've got to find out where this r is equal to 0. So we have 0 is equal to 1 plus 2 sine theta. Subtract the 1, divide by the 2. This is actually convenient because these are angles on our unit circle. First time this happens from 0 to 2 pi, that's 7 pi 6. And it will be negative 1/2 again later at 11 pi 6. Okay, so we're going to integrate over that range of angles. But the entire time we'll be integrating, r is negative. It's being drawn over on this side. Does this change how we set up our integral? The answer is actually no, it doesn't. This is quite interesting. Because the area is equal to, let's just integrate from 7 pi 6 to 11 pi 6. And the formula is 1/2 of r squared. This r is negative on this interval, but the square will get rid of the negative. So the formula works when the r is negative, and it works when the r is positive. Go back here and actually replace this with 1 plus 2 sine theta, and that's being squared d theta. You could do this by hand, right? You need to FOIL this, and then there's going to be a sine squared involved. You have to use the power reducing identity to finish it out. The shading is not actually doing anything for us because it's on the wrong side. Desmos can only do shading when the R is on the green arc, not on the red arc. But this is definitely confirming that we have the right window. 7 pi 6 to 11 pi 6 is, we're tracing out just that inner loop. And we wanted to get an answer. Capital A equals an integral from 7 pi 6 up to 11 pi 6. There's a 1/2 parentheses, something's going to get squared, and then a d. We'll use t again just so I don't have to type in theta. And we want to put the r function here, which is f of t. So there is our area of the inner loop, square units. All right, now I want to find the area inside the limacon but outside the inner loop. To do this, we're going to want to figure out, again, two angles, angle here and an angle here. Sweep counterclockwise, so we're going to go all the way around, and it's going to be doing all these wedges. But those wedges are going to cut into the inner loop. So if I do this integration all the way around to here, we're actually going to get the amount of space inside the entire limacon, including the inner loop. So if I want to have the answer be the area inside the limacon but outside the inner loop, then I'm going to have to do some subtraction. Now the angles we had in question, this was 7 pi 6, this was 11 pi 6, but I only use these numbers when I sweep this direction, which is not what I want to do this time. I want to start at this angle and sweep counterclockwise around until we get to this angle. Well, that doesn't make sense to start at a larger and end at a smaller, so what needs to be done is you need to adjust. You need to express this in terms of a smaller angle than this one so that we can increase to it. So we can't leave that as 11 pi 6 now. We got to go to negative pi 6 and then sweep counterclockwise around. Okay, so if I do an integral from negative pi 6 up to 7 pi 6 of 1/2 of this function, 1 plus 2 sine theta d theta, this integral will give me all of the area in here, including the inner loop. So from that, I'm going to have to subtract an integral of the inner loop only, which was the integral 7 pi 6 to 11 pi 6 of the same thing. Oops, I forgot the squares on square and square. This integral represents that inner loop. This should give us the area that we're after. Let's call the inner loop A1. And now we want to do the outer loop. We'll call that A2. And this will be an integral from negative pi 6 up to 7 pi 6. And then otherwise it's the same. Let's change this negative pi 6 up to t. And we'll change this from negative pi 6 up to 7 pi 6. And then as this varies, look at the area that we're getting. It's including the inner loop. And don't end at pi. If you end at pi, there's a little piece that we haven't finished, right? We've got to end at 7 pi 6. So this one integral will give us all of it inside there, including the inner. So that's what A2 represents. And then the area that we want would be A2 minus area 1. Area between two polar curves. Let's say we have a polar curve r equals f of theta, we'll say is the one that's wavy, and the one that looks more circular in this image we'll say is r is equal to g of theta. Then we have two angles from alpha to beta, and let's say that we're after this area that's between the two polar curves. One approach is to find out how much area is in this triangular wedge, and then you just subtract away from that this one. So do the orange minus the red, and you get what's left is just the piece that we're actually after. And you could set this up as an integral minus a separate integral, or you can just combine them into one statement. The area between two curves is going to be a single integral from this angle to that angle. 1/2 will be in front, and then so you do the outer r, and that needs to be squared, and then minus the inner r, and then that needs to be squared. Find the area inside the limacon, but outside the circle. Do this without using technology. So that tells us we're after this crescent. I do see some symmetry here. We could just go to the top half of it and then double our answer. We do need to find the angles where the intersections happen. To find that exactly, you set these equal to each other. Subtract 1, so we just get 1/2 equals cosine theta. This is true when theta is, typically when you integrate, you want to counterclockwise as theta increases. So we want a negative angle up to a positive angle. Definitely negative pi thirds and positive pi thirds are solutions to this. The area is going to be, let's use symmetry, so I'm going to double an integral from 0 to pi thirds. Then we have the 1/2, and then we have the outer. The limacon will be the outer. And that limacon equation is 1 plus cosine of theta. So there's the outer squared, and then minus, and then the inner squared, which is 1.5, and that needs to be squared in d theta. I know the instructions say do this by hand, but we just have to FOIL this, combine some constants. There's going to be a cosine squared you're going to do a power reducing identity on, and let's just get an answer here using Desmos. And this would be square units.